ideal scenario. So feel free to ask as many questions as you would like, and let us get started. So I didn't change the title. Boy, howdy, off to a great start. This is Diodes for Hobby Electronics. Starting off with some contact info. If you would like to contact the general email, it's electronicsosu@gmail.com. And then we have our individual officer emails. If you are not on the Discord server yet, feel free to hop on. I have some personal office hours in a Zoom room that you have the link to if you got emails for this meeting. Thursday, so tomorrow, 7 to 9 p.m. We have open officer positions, social media, webmaster, funding coordinator, and e-council rep. If you are interested in any of them, please send an email to electronicsclub@gmail.com. So again, I have online office hours. If you have any questions about the meeting content, or if you have general questions, feel free to stop by. I do not bite. If you'd like to follow along with the slides, some of these slides have some walls of text that are interesting to read. Feel free to click on the meeting slides. They should be up there. If you go to this website, our electronics club at osu.edu. All right. So our content overview for today in our deep dive. Oh, looks like we got a new feller looking at our meeting. So our content overview. So we're starting off. What is a diode? What does it do? How does it work? And those are our three kind of overhead and general theory questions. And then on the more practical side, a more recent Discord. Oh, that is expired. I will be sure to get a new Discord link by the end of the meeting. My apologies. All right. So on the more practical side, after we're done with theory and overhead, we're going to go in, how do we work with it? What can we do with it? And underneath that, some workshop examples, other applications, and then some thoughts on how to select your diode for your project. So number one, what is a diode? This is the way that I like to think of diodes. Common diodes, which are just the normal line with a little arrow, are kind of like a roller coaster line. You have to be a certain height to get in, and you can only go one way. That height for something called PN transistors is about 0.6 volts, which is why I have that little must be at least 0.6 volts to ride. So there are a whole bunch of diodes, I think a few more than the types of transistors. And we're actually interested in a few more kinds of diodes than we were before. Where before it was just BJT and MOSFETs. Now we have common diodes and Zener diodes. And it looks like Edward went ahead and posted a new Discord link. So there's common light emitting diodes. We use them all of the time. We just don't really think of them as like diodes. Zener diodes, something called Schottky diodes, photodiodes, varroactors, laser diodes, et cetera, et cetera. The two that we're interested in, and we'll be kind of going over more specific examples, are common and Zener. So the PN junction and the Zener diodes are mentioned here. They have two symbols. So the PN junction is just the single line, while the Zener is our little kind of like curly. It's slightly different than the Schottky, which has more of an S. So if you look at diagrams, you need to make sure that you're thinking of it as a Zener diode, a PN junction diode, or a Schottky diode. If it's a light emitting diode, it has two little arrows next to it. So how do they work? Again, semiconductors, the same way transistors work. So there's semiconductors of type P and type N. When they are biased a certain way, current is allowed to flow. You can see that in the forward biased or open door. So when it's positive to the anode and negative to the cathode, current is allowed to flow. When you flip it the other way, current is not allowed to flow. A good way of thinking about this is, again, using the pulley water system analogy that we used in the transistor meeting. If we apply a 0.6 volts kind of push to the anode, it opens a kind of spring or a gate, allowing current to flow. And when you try and go the other way, there's a block there that stops it from moving. And the terminology forward bias and reverse bias is used a whole lot in electronics. So that is something good to remember. That forward biased is towards the arrow, reverse bias is away from the arrow. So how do we melt common diodes? This is always a good question whenever we go to a new component, is how do we destroy it? And the way that we destroy a diode is by putting way too much current draw. So the diodes always have a voltage drop across the anode to cathode. And that drop is proportional to the current draw. So if we draw too much current, the thing melts. Because the higher the voltage drop, the more energy is lost in the diode through heat. So when there's a whole lot of voltage dropped, it means that a whole lot of heat needs to be dissipated, meaning that we melt diodes. And you can see there's a left-hand side too. So it's not a perfect kind of gate. A little bit of voltage is allowed to get back through. That's called leakage current. And if you have too much of the reverse, you also melt down. And so that was our common PN junction diode, or common diode. Oh. Hello, Zachary. If you'd like to watch along and catch up with the slides, go to Electronics Club at osu.edu, and in the top right, you'll be able to click meeting slides and keep up with everything we're doing.
Okay, thank you. Sorry, I had a lecture before this.
No problem. We are currently talking about how to melt common diodes and the differences between this PN junction diode, and now talking about Zener diodes. This is the other kind of diode that we're talking about here and is used a whole lot, and is used much differently than we would a PN junction or a Schottky diode. So a Zener diode is a two-way gate, so it's no longer a single way. But it is much easier to push forward bias than it is reverse bias. So to push forward, we only need around 0.6 volts. And to push in reverse, we need a much higher voltage. And that voltage is determined by whatever diode we're using. So if you look in the data sheet of whatever diode that you're using, it has something called a Zener voltage breakdown, or a VZ. And when we reach that VZ, then voltage is allowed to spring through the other side. So in the image there, you see one of the springs is much smaller than the other spring. And that is what gives Zener diodes its like special uses. So how do we melt Zener diodes? Well, same principle, draw way too much current. And you can see there's different kind of meltdown points for different VZs, or different kind of spring voltage requirements. Zener diodes are usually oriented reverse bias direction. So we can orient them like we do p-n junctions, where we have high going to low. But really, the interesting part of Zener diodes is the like harder to push down spring. So normally it's oriented reverse bias. And we'll see some examples of that later on. So what can we do with it? There are a couple of examples. We'll be going over examples for the p-n junction and for a Schottky diode, which is used essentially like a common diode. There's nothing special going on with the Schottky yet. So the one will take a few minutes to do are and OR gates. Two things that I thought you could do with a transistor, but you'd need two NAND gates. But you can do it directly with an and OR gate with diodes. And here is what that looks like. So starting with this example, we'll take 7 minutes to go through both of these. And I say through both of them because the way you get between an OR and an AND gate is just by reversing the diodes. So you can go to tinkercad.com and you can actually do this. So tinkercad.com. So the battery I have there is, I think you can look up like AA battery and then click 2 batteries. So let's kind of look at what's going on there. Well, we have 2 inputs, A and B, and we have our diodes pointing that way. Well, if both of them are off, then it looks like current is flowing from V out to ground. And if at least one of them is on, then it's flowing from, oh, my apologies. That was incorrect. If they're both off, then nothing is flowing into V out because there's no input current. If one of them is on, then something is flowing to V out. And if both of them are on, then something's flowing. If only B is flowing, then it's flowing. And you can look at that in the kind of bottom left diagram. That little open triangle is ground. All right. Is anyone following along in Tinkercad? Then I will allow you. Let's start back up at 6:22. Let's call that. And then we'll switch over to the AND gate. If you have any questions, post them in chat. I'm going to run downstairs and grab some water real quick. Has anyone gotten it to work yet?
Almost.
All right. I usually include the resistor values there. I think the one connected to the green is a 220 ohm, and then the one connecting the LED to the ground is a 10 ohm resistor. I forgot to put that up there.
All right, got it working.
Awesome, good. Then let's go on and move to the AND gate. So all you need to do is switch around the diodes, and then in the upper left, change it from voltage low to voltage high, or ground to the 3.3 volts. So what's going on here? Well, when both of them are low, it means that we are forward biased, meaning that current is flowing from our battery into VA and VB, which are held at ground. If VA is activated, then it's reversed bias at D1, but it's still forward biased at D2. So this means that our battery is still being pulled down to ground. So our current is flowing from our battery to VB. But when both of them are activated, it means that they're both reversed biased, meaning that instead of going to ground, the battery now goes to V out. So we'll take just a couple of minutes on this. So I will come back at 6:25. All right. quick note. LEDs are light-emitting diodes. That's why they have an anode and a cathode, and they only work if they're going one way. Only if there is a forward biasing from the anode to the cathode. And that is also a good example of diodes just blowing up if you add too much current, because LEDs blow up all the time. At least I personally blow up LEDs all the time. I don't know if you are some magic man, but let's see. So the acronym up there means what can I do with it? And here's another thing. In our workshop, I believe 2 workshops ago, not last workshop, but the one before that, we did some motor control where we used an Arduino to check for a button input. And then if there is a button input, we outputted a 5-volt signal to this MOSFET. And this MOSFET was controlled by this much larger 9-volt battery, which controls our motor. But when we're doing this, and we shut our motor off, the magnet inside of it, according to Ampere's law, I believe it is. I am a physics major, I should know this. When a magnetic field collapses, according to the kind of right-hand rule, there's a cross product there. It means when a magnetic field collapses, there is a large backwards electric field. So a large voltage gets shot back into our Arduino, and that can break our Arduino or break our MOSFET. The way to remedy this is by introducing a Zener diode. When we have that Zener diode, I think I have Griffith's like right over here. Yep. It might be like just on one of. I'll look at that later. But the Zener diode essentially acts as a kind of water breaker, like in a wave pool. It stops it from oscillating back and forth and make sure that it's not doing this. You can see the 2 graphs, the without diode and the with diode, where without the diode, the voltage kind of oscillates like this. And those kind of large voltage spikes are much larger than the 9 volts and can break stuff. But with the diode, it just goes down. And so this uses a Schottky diode. So Schottky diodes work essentially like common diodes. We'll see the difference in them a little later on. The reason I didn't go over Schottky diodes is because they are essentially used in most of the cases of common diodes, except for when you have fast switching or kind of special cases. Unlike Zener diodes, which are completely different. So this is the kind of other applications portion. So this is no longer kind of like physical examples that we can do, but things we can think about and kind of look through. So this is a common diode. It's called transient protection. It uses the same kind of idea of the flyback diode. Whenever we have an inductor or a relay here, there's always the chance of having the large negative spike, and that can destroy digital components. So if we add a diode there, when we have that big negative spike downwards, our diode says, no, we're meant to be biased this way, and it ensures that we do not have a negative spike. So the kind of takeaway from that is you can add diodes to stuff to make sure things don't blow up. That is a common use of diodes, is to make sure in power electronics that things are not going blammo. And as an example of things going blammo, there's a use for diodes called half and full wave rectifiers. So A half-wave rectifier is just a diode in series with or in parallel. That is the exact video, yes. The full bridge rectifier that we will get to. But the half-wave rectifier here takes in an AC voltage, yeah. So we have a kind of sine wave going on. And our goal is we want to convert it into a DC voltage. So instead of a sine wave oscillating between positive and negative, we want just a flat positive. And we get there a little bit when we do a half wave rectifier. So whenever it's positive, it's allowed. And then we get down, and negative is not allowed. So we have just 0, and positive is allowed, negative is not allowed. And we continue forward like that. If we have something called a full wave bridge rectifier, we have 4 diodes to make sure that even when we're going down, we have the other diode to supply the negative voltage going like that. My original idea was I could stream this 4-minute electro boom video and we could watch it together. But my internet is not that good, and Zoom is not that great of a transmission. So I will post the video link in the Zoom chat, and I highly recommend you take the 5-minute break here to watch this really good electro boom video about this full wave or full bridge rectifier. There we go. So I will find the link. If you are following along, you should be able to just click on the link.
Hi, I want to make a.
All right. So I have posted it in chat. So we'll take the 4 to 5 minutes. Please look at the video. It is very good and does a full service and a kind of full explanation to the full bridge rectifier, and has a lot of really good kind of safety tips. Electro boom is great. So we'll meet back here at say 6:37. All right. Hopefully you have been properly educated by the wackiness that is Mr. Electro Boom. Check out his other videos if you're interested. He is amazing. All right. So we have one more use for common diodes here. And this is ROM, or read-only memory. This is a concept that is explored in detail in ECE 2060, digital logic. So it looks complicated, but look at each line individually and it becomes a little easier. Only one of the numbered switches are turned on at a time. So if we turn on, say, 1, the 1 switch, what's happening is that we're going across the line. And it looks like the diodes are pulling the the leftmost LED to ground, then the next LED to ground, the next LED to ground, and the first LED to high. So when we switch 1, it displays the binary number 1 on the bottom. If we look at, say, 5, what it's doing is pulling the first LED to ground, and then the third LED to ground, which displays 0, 1, 0, 1, and the LEDs on the bottom. The bottom, you'll see you have that little diode symbol with the 2 arrows next to it. Those represent LEDs. So when we switch 5, we have 0, 1, 0, 1, which is the binary number for 5. To wax poetic, let's display the number 7. When we flip 7, it pulls the first LED to ground, and then the other 3 LEDs to high. So it displays 0, 1, 1, 1, which is how you display 7 in binary. Pretty cool. And you can have not only like these 10 specific orientations, you can display like any kind of binary number you want. So you can store like the number 507 if you have enough lines of binary numbers, or enough like vertical lines. So this is used in kind of digital logic for a number of applications. Bring out the diodes when you don't want them. For specific kinds of packages, specifically, I think they're called like reprogrammable ROM or something like that. Yes, you can absolutely reprogram what is stored inside of it, and then it becomes read-only again. But for this like physical kind of rigid system, this cannot be reoriented. But yeah, you are absolutely correct that there are ROMs where you can change what is stored. So this is a application of a Zener diode. It's important to make stuff. Make sure that stuff does not blow up when you accidentally switch up what ground and high voltage is. So if you plug in your socket incorrectly, making sure that things don't go boom. So when the positive end of the Zener diode, when there's a high enough reverse bias, the Zener diode allows current to flow, which trips the fuse, causing a break in the circuit. So this makes sure that things don't blow up because you applied way too much voltage. Arduino does not have this. So if you apply too high of a voltage to your Arduino, it will just break and die. So don't do that. Don't apply like a 9-volt battery to your like 5-volt thing and then to ground because it will not be pretty. It won't blow up, but it'll just be broken, which is unfortunate. You always want the big like boom shocks because then you know something is broken. But most of the time things break and then you don't know why and you don't know how. So another use is a voltage regulator. If we apply a Zener diode in parallel with our load, and we have some resistance, we can have a much higher V in and regulate it to whatever the Zener voltage is. So we have a high DC voltage at the bottom there, 12 volts, and we regulate it to 5 volts. This usually comes in like little 5 volts regulator packets or packages appear here. There are certain components that really like specifically 5 volts. If you're trying to control an AT-Tiny85 or certain microcontrollers, they will only accept 5 volts. So if all you have is AA batteries or a 9-volt battery, then you need a voltage regulator to make sure that things can operate properly. Of course, there are other ways of changing voltages. This is just one of the ways. Specifically, it dissipates the excess energy through heat, which is a problem if you draw too much heat. That's why it has that little heat sink there. Another use for Zener diodes is a kind of simple voltmeter. So current only flows if the Zener voltage is exceeded. So you can see the resistors are progressively higher, showing a kind of lowering of the voltage. So it shows the LEDs at the bottom only light up if you have like the 5, 6, 9, 12, 15, 16 volts. So this might be useful if you want the circuit that you're working on to operate a certain way when you're at 5 volts, but a different way when you're at 15 volts. Maybe you want it to shut off. So similar to the transistor, we have a laundry list of extra applications. So a voltage dropper, a voltage regulator, adjustable waveform clipper, adjustable attenuator, diode voltage clamp, diode switch, voltage multiplier or a boost converter, if you apply also an inductor. A voltage tripler or a quadrupler, where you can get really high voltages using a clever orientation of diodes. Battery backup or AM detector, AM like radio waves. A certain diode configuration allows you to detect that. I forgot to put a comma in there. There's even more for Zener diodes, waveform modifier and limiter, voltage shifter, or voltage regulator booster. All of these applications will be included in a PDF that I will post to the slides Google Drive link that we have up there. These are all from a chapter in this book that I steal content from called Practical Electronics for Inventors. A lot of the pictures came from the diodes chapter in here. So if you'd like to make any of these, the whole diagram and explanation of these diagrams are all in here. And there's even more diodes that I didn't even mention. The Vera actor, the Photoshocky, impact gun tunnel pin diodes, et cetera, et cetera. I think there's also laser diodes, which are like the laser pointer things. A whole lot of kinds of diodes. So what can I do with it? Picking one. There are a number of diode packages. They come in you can get like an IC where it's just like a diode across, diode across, diode across. If you have a whole lot of diodes, they come in individuals. They come again with the little heat sinks already on there because diodes produce a whole lot of heat. There's packages with bridge rectifiers already in there, so you don't need the 4 individual diodes. There's certain ones with dual diodes that already have 2 diodes connected. And then, of course, the surface mounts. And then the Zener diodes have separate kind of packages as well. And I have a little note there that says Schottky diodes are used for fast switching. So if you have a certain high frequency, eventually the normal common diodes kind of break down and don't work as well. So if you have a high frequency signal and you need to switch between high to low voltage really fast, use a Schottky diode. That has the downside that Schottky diodes explode much easier because they have a lower voltage drop. Some extra goodies. I included 4 more walls of text if you'd like to look at the slides and look over that. This will also be in the PDF that I'll post later. Here is a kind of laundry list of different diodes, common and Schottky, and their kind of range values of when you can use them and their specific names. So if you go on like Jameco, you can order these for your specific project. So challenge those ANDs and OR gates we used earlier. You can apply any number of extra inputs and still kind of make it work. So these are 3-way gates, but if you applied a 4th line, you could have 4-way gates, and those have the combined properties listed there, where all of them have to be on, or only one of the multiple have to be on. So feel free to try this out on your own in the Tinkercad, or if you have a whole bunch of diodes with you. I think I made the mistake of trying to order common diodes, and I ordered a whole bunch of Zener diodes and tried to make some physical examples for today and realized that nothing was working. So make sure that you're getting the correct diode for whatever application you're doing. Any questions? All right. Please enjoy this XKCD comic, and we will have another meeting next week. I am not sure of the topic yet, but that will be announced in the newsletter on Monday. All right, y'all are free if you have no questions. I have office hours tomorrow, 7 to 9. Feel free to stop by. Yeah.
Thank you.